Solutions on a technological level, on a market level, and not least at a societal level. There are many different technologies that will take us further, but not all solutions fit all problems, and not necessarily at the same time either. So how to prioritize? How do we know what to do and when and at what scale? This is what we're going to elaborate on during the next small hour. The first speaker has taken on the task on reflecting on the question of timing and scaling. And he steps up this time from the expert panel on the first row to the podium in a short while. Volker Krey, he is Research Group Leader for Integrated Assessment and Climate Change at IIASA, the International Institute for Applied Systems Analysis in Austria. That's why you call it just IIASA, much easier. Now, Volker here, he is widely regarded as a leading expert in integrated assessment modeling, focusing on the interplay between energy systems, climate change, and sustainable development, so all three in at once. So, Volker Krey, I just wonder, what is your analysis on the ways forward, not only one way, but the ways forward, knowing that climate overshoot is just around the corner? Now, everyone else has been accepted an applause at the beginning of their speech, so will you. So, take it away, Volker Krey.
Yes. Thanks a lot for the kind introductory words. Good afternoon also from my side, and thank you for the organizers to give me the opportunity to speak here. I'm glad to hear that there seems to be consensus that despite the changing geopolitical environment, climate change and dealing with it remains high on our agenda. Let me just repeat this. This is some of the latest measurement data. As you all know, we have in principle been exceeding 1.5 degrees last year. That doesn't qualify as exceeding 1.5 degrees in the sense of the Paris Agreement, where the long-term trend really matters, but that is around the corner. So 2030, if we continue current trends of warming, is probably when we're going to from the long-term perspective, or from the long-term trend perspective, exceed 1.5 degrees. So we are now basically in a regime to manage overshoot. So basically we will exceed and then need to figure out how to bring down temperatures again, limiting also the biophysical impacts and the economic damages resulting from it, where the estimates have basically gone up over recent years. So let me first start out with some high-level insights from pathways analysis, specifically with a European perspective. I'm drawing here on material that was compiled by the EU Scientific Advisory Board on climate change, feeding into the European strategy towards neutrality and setting the 2040 targets. I like this because it's not just like one analytical study, but it's really an assessment of what's out there. Obviously, these targets need to meet the 55% target. These pathways need to meet the 55% target that Europe has adopted for 2030, and then the climate neutrality by 2050. But the question is, of course, how to distribute this over time. The good news is, there is not just one pathway that gets us there. These pathways share some commonalities, which I'll comment on, but there are also a number of choices, which is probably good news. That means also every country, every legislation can kind of pick and choose to some degree, and that of course relates also to what other non-climate environmental and social impacts these pathways would imply. The panel here, the advisory board specifically picked out 3 illustrative pathways, one with a strong focus on renewables deployment, one with a stronger demand side perspective, so limiting consumption, improving energy efficiency to bring down energy consumption, and a more mixed approach which employs a more diverse set of also supply side measures. The outcome of this was a recommendation of 90% to 95%, which a year ago the Commission adopted as a recommendation for the 2040 target. That process hasn't finished, but let's unpack that a little bit. There are a few insights which are very robust and that we've heard about over the course of the day, decarbonization of the electricity sector, largely based on renewable energies, strong electrification of the demand-side sectors. So we've heard a lot about this. Very soon, phasing out coal from the system, followed by natural gas eventually. But of course, there is also variation, as I already highlighted, in terms of how heavily to rely on each of these components. Reducing energy demand, I mean, we'll need to do something, but we can put more emphasis, also varying across sectors, and what that entails I'll come to in the next slide. One important insight is reducing non-CO2 emissions, foremost methane, short-lived climate forces, because that will help us to moderate the overshoot of temperature because of the short lifetime of methane and the contrails that we've heard about recently. That's another of these kind of short-lived forces that if we can mitigate them, there's an almost immediate or very short-term effect in terms of limiting temperature increase. So that's helpful. That involves energy, but also agriculture and waste management. Scaling up of bioenergy and hydrogen, these are actually two components of the path where the pathways diverged quite a bit. I mean, as you all are aware, bioenergy has other roles to play, other ecosystem services to be provided by forests and other land sources, as well as biodiversity being an important issue. Hydrogen has had its ups and downs. It probably has niches where it's very difficult to get around it. Also, just as a side note, hydrogen, if it leaks, one needs to be aware that there is an indirect climate contribution. It has a global warming potential associated with it because it ends up prolonging the lifetime of methane in the atmosphere, and that in itself is a potent greenhouse gas. So, meaning if hydrogen, we should be conscious about reducing losses along the value chain as much as possible, and then, of course, also bring methane emissions down. And then last but not least, scaling up carbon removals in the range of 150 to 600 megatons by 2040. That includes the land sink, so for reforestation, afforestation, and here we need to be conscious that climate change impacts may actually limit that option severely compared to what the models tell us at the moment, simply because they may limit the uptake or the ability of forests and other land to take up more CO2. So also technical carbon dioxide removal options may be required that are less vulnerable to climate change impacts. When it comes to picking among the different strategies, one thing that the report heavily emphasized, and there's earlier analysis on that also by the IPCC, is that all of these options have then implications for other sustainability goals in the social, environmental, and economic domains. And one high-level insight is, there is, of course, nuances to keep in mind, that demand-side focused measures tend to have larger benefits in other domains. We heard about energy security, and that wasn't really brought up as an important strategy in terms of managing energy security. The energy that you don't use is basically you don't have to import, right? So that's one of the clear examples where demand-focused strategies might be helpful. They're sometimes harder to get off the ground, but these considerations again important. Then we are acting under pressure, under time pressure. So scaling or scalability of solutions matters, and there is increasing evidence that technologies with some characteristics, and notably those that are modular and small in scale, they tend to scale faster and they tend to learn faster, simply because you don't have super large, lumpy investments of which you have only a few, which allows you limited opportunities for experimenting with the design, while small-scale solutions, the innovation cycles tend to be faster. There's more room for experimentation. On top of it, there is evidence that these small-scale technologies also generate larger other societal benefits, including employment effects, returns on public R&D, also equity in terms of access tends to be higher for small-scale solutions compared to, or small-scale modular solutions compared to lumpy, large-scale investments. One aspect that the report did not move into, but that there's also growing literature accumulating on. At the moment, we're focusing on operational level emissions, but of course, eventually the embodied emissions we also need to target. You see here an example of an analysis for the European residential sector. At present, roughly 90% are operational use emissions, 10% are embodied. Once you decarbonize the electricity or the energy supply system, the embodied emissions remain unless you adopt additional measures. So those you would typically classify under circular economy measures to further curb emissions, these embodied emissions. So this will become eventually very relevant once you're approaching carbon neutrality or enabling you to do so. I mean, even under current policies, circular economy measures would allow basically cutting something like 40% of total emissions, and then it becomes really critical once you have a decarbonized supply system, then it's basically another 60% of that embodied emissions of the residual can help removing. Few words about the motivation and why it might be a good idea, despite the current geopolitical tensions, continue investing in mitigation, and that is climate change is not going to stop here. And all the evidence that I'm seeing is basically showing that climate impacts are getting significantly larger. There is a larger body of literature now that does econometric studies. And if you put the numbers together, this is basically the damages are here shown in red, and in this greenish color, the corresponding mitigation estimates to get to this level. So current policy extrapolation down to 1.5 degrees with very limited overshoot. Then you see almost in all of these cases, the mitigation costs end up being significantly lower. What is important to note is there is this shaded area that gets to very, very large numbers, so tens of trillions of dollars, and that's basically the 90% confidence interval on the damages. If the climate system ends up being unfriendly to us, and unfriendly here not meaning kind of a 1 in 1,000 possibility, but this is a 1 in 10 possibility. The red line here is a 1 in 2, so basically it's the median expectation, what the damages may turn out to be. So then you see the situation actually very much skewed towards risks of much higher damage costs compared to what mitigation would cost us. This is just a set of alternative econometric studies, and this insight that mitigation really pays off is pretty robust across the current available studies. Obviously, that then immediately raises the question, who pays for it? What you saw previously was global numbers. And if you do a thought experiment about fairly distributing the damage costs as well as the mitigation costs, according to a variant of polluter pays principle, then you see this is basically all regions in the global north. This is global south, mostly affected by climate change impacts. And you see actually the mitigation costs are very small, and the transfers related to the mitigation, while loss and damage compensation is at least an order of magnitude bigger. There is more variance how one can do this, but it really emphasizes the need to come to an equitable distribution of the effort and costs of both the damages and the mitigation. Last point that I'm going to pick on here is basically the perspective of risk management. I mentioned that there are median estimates, but there's also confidence intervals. And we see that carbon dioxide removal is a strategy, and that includes both land-based options to remove carbon and technology-based options to remove carbon, such as direct air capture and bioenergy with CCS. There is considerable uptake in pathways that were featured in the 6th assessment report of the IPCC. But if we're not happy with a 1 in 2 chance to eventually come back to 1.5 degrees after overshooting, then you would actually need to add a lot of CDR on top of that as a risk management perspective. This would get the chance to 1 in 10, and this is additional carbon dioxide removal, 600 gigatons at global scale. That would get us to more than 1,000 gigatons. So a very considerable extra effort to manage risks. That brings me to my concluding slide. So just to summarize very briefly, reducing short-lived forces, methane foremost, very important to curb temperature overshoot, limit the residual gross CO2 emissions, targeting embodied emissions. Focus on technologies that rapidly scale. Let's not rely on options of which we know that the likelihood is very shallow that they will actually scale up. Maximizing synergies with other objectives, equitable access to mitigation adaptation finance, and then developing CDR not only to compensate residual emissions elsewhere, but really to manage climate risks is important. And in that context, let me spend 10 seconds of doing some self-advertisement. We have in 6 months from now a conference featuring the topic of overshoot and overshoot management at IIASA in Luxembourg. So if anyone's interested in this topic, we'd be very happy to welcome you. Thank you.